This is a question from AQA A-level Chemistry. It is from paper 3 based on the required practical assessments, and this one is based on RPA9. I'm going to recommend you pause, have a go at each section for yourself first, and then you can review. So let's take a look at part A. Moving on to part B. Moving on to part C. Then we have part D. Then we have parts E and F. Then we have part G. And finally, we have part H. 16-mark question, a very, very big one. Okay, so now you've had a chance to try it for yourself, let's take a look at the answers. This question is about pH. Pure water dissociates slightly, and we're given the enthalpy value for it. Delta H is positive 57 kilojoules per mole. We're given the equilibrium constant, and we're given the ionic product of water. First question, why is H2O not shown in the Kw expression? Well, the key to this is recognising that there is only a very slight dissociation. And what that means is, from your water, only a tiny fraction of it will actually dissociate. Now, that means that when there is dissociation, the H2O concentration is largely constant. It barely changes to the point that we can assume it to be constant. And as I've already said, that's because it's much higher in concentration than the H plus and OH minus ions that have been dissociated. Moving on to part B. Why does the value of Kw increase as the temperature increases? I'm going to bring over that data that I've already touched on. This is forward reaction endothermic, but we would know it's endothermic because we are actually dissociating things. We're breaking them apart, the H plus and the OH minus ions. That's always going to require energy. But that positive is incredibly important. The fact it's endothermic is incredibly important. If I take the expression Kw is H plus times OH minus, and we recognise that dissociation is endothermic, we know the forward reaction is endothermic, and that means the equilibrium will shift to the right-hand side as equilibrium increases. Now, that means we're favouring the endothermic reaction. So we've got the explanation top right and the answers we would write down here. But mathematically, you can see that Kw would go higher because greater dissociation would mean more H plus ions, more OH minus ions. You're multiplying together two higher concentrations, so you've got a higher Kw. Moving on to part C. Give the expression for pH and give the pH of pure water at 50 degrees C. Give your answer to 2 decimal places. Explain why water is neutral at 50 degrees C. Well, the expression, that's the definition or expression for pH right there. Obviously, that is a lowercase p, capital H, one to watch out for on that one. In terms of the calculation, we have got Kw is H plus times OH minus, and we've got from earlier in the question our Kw value for water at 50 degrees C. Now, because we know that when one water molecule dissociates, it gives one H plus and one OH minus, we can assume that H plus concentration equals OH minus concentration, so Kw is equal to H plus squared. Now I can rearrange that to make H plus the subject, and H plus is going to be root Kw. So H plus is root 5.48 by 10 to the minus 14 from the table provided. And that takes us to a value of 2.34 by 10 to the minus 7. We've written the expression for pH up top, so pH is negative log to the base 10 of that 2.34 by 10 to the minus 7. We put those figures in and we get a value of 6.63. We know the answer is going to be close to there because we're on 10 to the minus 7. So always double check your answer to see if it's reasonable. Similarly, it's the pH of water. It's not going to deviate too far away from 7.00. Okay, on to part D. We've got here a pH meter is calibrated using a calibration graph. To create the calibration, the pH meter is used to measure the pH of separate solutions, each with a known accurate pH, so different buffer solutions. And we've got the calibration curve provided. Give the true pH value when the pH meter reading is 5.6. So we go to our pH meter reading of 5.6, draw in the construction lines, draw across and draw down, and we can see that if we measure 5.6, calibration curve tells us the value is actually 5.5. Moving on to parts E and F. In E, suggest why the probe is washed with distilled water between each of the calibration measurements. Well, what we don't want is remnants of previous solutions remaining on our bulb in the pH probe. So it's to avoid contamination from the different solutions. The calibrated pH meter is used to monitor the pH during a titration of hydrochloric acid with sodium hydroxide. Explain why the volume of sodium hydroxide solution added between each pH measurement is smaller at the end as the end point of the titration is approached. So you'll know this from probably one of the first titrations that you did back in year 12, that once you get near to your endpoint you've found in your rough titer, you will add dropwise. It's because you don't want to miss the endpoint. A small change in volume has got a huge effect on pH when you are close to the endpoint. And again, you'll recognise that in pH curves, as you can actually see on this one, where there is a very steep change for a very small change in volume. But let's move on and look at part G. Here is the pH curve for HCl with sodium hydroxide, and here are three indicators: bromocresol green, phenol red, and thymolphthalene. Each of them have got a pH range over which colour changes from bromocresol going from yellow to blue, phenol red, yellow to red, thymolphthalene, colourless to blue. Why would all three indicators in table 2 be suitable for this titration? So what you've got to do here is look at the range over which the colour changes, because you want to get a single drop making that difference to get you between 3.8 and 5.4, or taking you from yellow to green to blue, maybe getting it in the green, but certainly that one drop that takes you from yellow to blue is going to give you the accurate endpoint. Now, actually, because this is a strong acid and strong base, all of them have a colour change within the vertical part of the graph. And that's the answer that we're looking for there. Moving on to part H, big calculation. 36.25 cm cubed of 0.2 molar sodium hydroxide is added to 25 cm cubed of 0.15 molar HCl. Calculate the pH of the final solution, and we're given the Kw value at 25 degrees C or 298 K. So the first thing, going to work out the moles of OH-. We've got a concentration and we've got a volume. The volume I've divided by 1,000 because I need to convert it to decimeters cubed, and I'm going to multiply that by the 0.2, and you can follow the colours through on this to see precisely where they're coming from. That tells us that we've got 7.25 by 10 to the minus 3 moles of OH- as we begin. Next, I'm going to work out how many moles of H+ I started with. Exactly the same procedure. I've got a volume and a concentration. So 25 cm cubed, divide that by 1,000 to convert to dm cubed, multiply that by the concentration of 0.15, and that tells us we've got 3.75 by 10 to the minus 3 moles of H+. So after we've done that, we need to look at what's in excess. Well, we've got more moles of OH-. So I know that this is going to be a base. I know that my pH is going to be above 7. But how many moles in excess is it? Well, H+ to OH- is in a 1-to-1 ratio. So 3.75 by 10 to the minus 3 moles of H+ will have reacted with 3.75 by 10 to the minus 3 moles of OH-, and that means that we are left with 3.5 by 10 to the minus 3 moles of OH-. That's my moles. I need my concentration. So what I've got to do here is take my number of moles, and I am going to divide it by volume. Now the volume is the combination of the two solutions combined. So we've got 36.25 cm cubed and 25 cm cubed. So we've got to do that as 61.25 centimeters cubed. But again, we've got to remember to divide that by 1,000 because we need to convert it to decimeters cubed. That gives us an OH minus concentration of 5.71 by 10 to the minus 2 moldy M to the minus 3. We're still not there. We've got a way to go yet. I don't want my OH minus concentration. I want my H plus. Handily, I've been reminded what the Kw value is, so I know I'm going to use that expression. If Kw is H plus times OH minus, H plus concentration is Kw divided by OH minus concentration. Kw, from the data provided, 1 by 10 to the minus 14, divided by the concentration I've just calculated, 5.71 by 10 to the minus 2. That gives me an H plus concentration of 1.75 by 10 to the minus 13 moles. I then do my pH calculation, giving me a pH of 12.76. Again, ask yourself, is that reasonable? It certainly fits, 12.76 relating to 10 to the minus 13. And also, we are dealing with a base. We're dealing with OH minus in excess. We would expect our pH to be above 7. So with both of those things in place, we can be confident with that answer. That takes us to the end of this question. Thank you for listening, and goodbye.